So the lesson we're going to go through today is on implicit differentiation. So this will allow us to find the derivative when the formula is not y equals. If we're able to convert the formula to y equals by rearranging it, that's okay. We could do that and then take the derivative with our normal rules like we've already done. But this formula or this method will allow us to solve when the formula is not y equals. So it allows us to find a derivative when equation is not y equals. So what we have to remember about this is we're differentiating with respect to x. So every time you differentiate with respect to x, for example, the derivative of x squared with respect to x is just 2x. But anytime you're differentiating a term without an x squared in it, for example, a y, what you need to do is you need to think of y as a function of x. So the derivative of 4y would be 4, but then the derivative of y itself would be y prime. So that's kind of how we're going to tackle this lesson here. So again, sometimes it is possible to solve for y. And if you do that, then you just go through and use your normal rules. So for one example, we have y equals plus or minus 25 minus x squared would be the equation of a circle if you were to rearrange y equals x, y as a function of x. This formula would turn into that formula. And then if we were differentiating this, we would just use our regular chain rule because we have a function inside of a function. But what we want to do is when the function is not easily able to be converted from not y equals form to y equals form, we want to be able to have a way to find the derivative. Okay, so let's go through some specific examples on how to do this. So when we're differentiating with respect to x, we just take the derivative normally. This is with respect to x, and the variables or the expression I'm trying to take a derivative of just matches in that variable. So the derivative of x cubed is just 3x squared. But when I have a variable that doesn't match, we would do the derivative of the variable, which is 3y squared, but then we would have to do the derivative of the inside part. And the inside part that I'm referring to is y, because y is a function of x. So every time I do a derivative, the derivative of y would be f prime of x or y prime. So this term here represents y prime. So when we look at the next example, same idea. We're taking the derivative of x with respect to x, which means that's just a 1. When I want to take the derivative of 3y with respect to x, my derivative would be 3, but then the derivative of y would be y prime. When I have two functions put together where there's y's and x's, that's two functions put together, so we need to make sure we're using product rule like we're normally used to. So the derivative of x is 1. The derivative of y squared, we'll get to that when we do the second part. So this is the derivative of the first times the second plus, leave the first the same.
If you're still in the building, can you call the office? You should call the office, please.
And then we leave the second function, we leave the first function the same. The derivative of the second function is 2y, but because I'm differentiating a y term, I need a y prime. So that's how we're going to differentiate with respect to x with implicit differentiation. Okay? So when we're doing it and we have an expression, these are implicit differentiation with expressions. Differentiation of expressions. But now what happens if we have implicit differentiation with an equation? Okay? So what our plan is going to be is to differentiate both sides with respect to x. What we're going to do is any of the terms that we find that are dy dx or y prime, we're going to move them to one side of the equation. And our goal is to solve for dy dx because this represents our derivative. So let's look at this example. Find the derivative given that here's my function or expression or relation. We want to find the derivative of this relation. The derivative of y cubed, 3y squared, because it's a y, the derivative, y term, the derivative of y is y prime, plus the derivative of y squared is 2y. The derivative of y itself is y prime, so we're kind of using chain rule on all the y terms. The derivative of negative 5y is negative 5, but the derivative of y itself is y prime, minus the derivative of x squared is 2x, which equals, and the derivative of negative 4 equals 0. Now my goal in this problem is to solve for the derivative, which are these y prime terms or dy dx terms. So I want to group them all on one side. So I'm going to leave them on the left and move all the other terms to the right. 3y squared y prime plus 2y y prime minus 5y prime equals 2x. Once we move that term over, all these three terms have a y prime in it, so I'm going to factor that y prime term out. I'm going to get 3y squared plus 2y minus 5 equals 2x. And then my goal is to solve for y prime by dividing by that last term, 2x divided by 3y squared plus 2y minus 5. So this expression represents the slope of the tangent line to curve y cubed plus y squared minus 5y minus x squared equals minus 4 at any given point xy. At the point xy. Okay, let's keep going. I give you an equation. I want to find dy dx. You'll notice here x and y are mixed, so we have to do implicit differentiation. So we're going to follow those same steps and do this process again. Okay, so differentiate both sides. Derivative of x squared is 2x. The derivative of y squared is 2y, but because y is a function of x, we need to do the derivative of y, which is y prime. The derivative of 25 is 0. We move the terms over, so subtract 2x, subtract 2x. 2y, y prime equals negative 2x. So y prime equals negative x. And I want to solve for y prime. So I'm going to divide both sides by y, and this is my expression. Now when I want to find the slope of the tangent line, my m tan is given by minus x over y. So my m tangent, my slope of the tangent at a specific point, 3, 4, would be given by minus 3 over 4. So you're going to notice that we're using both the x and the y coordinate instead of just the y coordinate like we've seen before. Y minus the y coordinate of my point equals my slope, x minus my x coordinate of my point, and then I've written the equation of the tangent line to the curve at the given point, and this is a representation of my slope or my derivative. Okay, this one I will let you try, and the solutions will be posted. Let's try these examples. So the derivative of 2y cubed is 6y squared, derivative of y prime, plus the derivative of y squared is 2y prime, minus the derivative of the last term, minus 2x squared, we bring down the 2, minus 4x, equals the derivative of 0, which is 0. We want to group the y prime terms together, so I'm going to move the 4x to the other side. So I add 4x to both sides. I factor out the y prime, and I'm left with 6y squared plus 2y equals 4x. And then to solve for y prime, I divide both sides by 6y squared plus 2y. So essentially, anytime you're doing the derivative of a y term, you need to have a y prime in there because y is a function of x. Okay, derivative of y to the fourth, 4y cubed. Derivative of y is y prime, plus the derivative of y cubed is 3y squared y prime equals the derivative of x to the 5 is 5x to the fourth plus the derivative of x is 1. You'll notice that the y prime terms are already grouped on the left. We factor out the y prime, write what's left over, and then our last step is to divide. Y prime equals 5x to the fourth plus 1 divided by 4y cubed plus 3y squared. So this is the main idea of implicit differentiation, and the difficulty of the questions can vary quite significantly. So you'll notice here, we've talked about the equation of a circle. This is an equation of a circle centered at 0, 0 with radius square root of 4, which is 2. So that gives us kind of like a relation here, where it's not really a function we're dealing with, it's a relation. I mean, I could isolate for the y, but I don't really want to, okay? You can have examples of ellipses, examples of hyperbolas. You're going to notice hyperbolas look really similar to ellipses, but they're both, one is positive for the ellipse and the middle of the other two is negative for the hyperbola. When you get to the circuit goal, you'll know it's a circle because these two coefficients will be the same. And then we know our equation of a parabola. This one, instead of it being a parabola that opens up and down, this might be the parabola that opens up right or left. Okay? So in this example, they ask us to find the derivative for just some general ellipse formula. So now every time you see the variable a, it's just a number, and when you see the variable b, it's just a number. So we call those kind of parameters, and x and y are our main variables. So what is the derivative of x squared over a squared? So 1 over a squared is like a constant, so we just pull it out, times the derivative of x squared, which is 2x, plus the derivative of 1 over b squared. Well, that's a constant multiple, it gets carried out. The derivative of y squared is 2y times the derivative of y, which is y prime. And this equals the derivative of 1, which is 0. So my goal is to solve for y prime. So minus 2x over a squared, when I move that term to the right, this will equal 1 over b squared times 2y y prime. My goal is to solve for y prime. So y prime equals negative 2x over a squared. I'm going to divide it by 2y over b squared, which will be the same thing as multiplying by b squared over 2y. I clean that up a little bit. I get minus xb squared over 2, whoops, not 2, because we canceled the 2 out, over a squared y. And that would represent my slope of the tangent line at any point on the original function, which was in an ellipse. Okay, this one you can see that the coefficient of the x squared is 1 over 5. The coefficient of the y is a 1. There's a negative sign in between them. This kind of tells me that I have a hyperbola happening. So that's an implicit function because x's and y's are mixed. So I'm going to kind of rewrite the function before I take the derivative of it, just to kind of see that it's a constant multiple and I don't have to worry about quotient rule. The derivative of x squared is 2x, but I carry through the 5 because it's a constant multiple on the bottom. minus the derivative of y squared is 2y times the derivative of y, which is y prime, equals 0. I move the term over, 2y, y prime, I add it to both sides, equals 2x over 5. And then finally, I want to solve for y prime, so I'm going to get rid of the 2y. So I'm going to divide both sides by 2y. So I'm going to get 2x over 5 divided by 2y, which means y prime equals 2x over 5 times, that's 2y over 1, so this would get multiplied by 1 over 2y, which would give me x over y, and the 2's cancel and you're left with a 5. That represents the slope of the tangent. I want the slope of the tangent at a specific point. I sub in my point, 5 for the x, 2 for the y, and that works out to 1/2, which represents the slope of this line here that they've drawn in at that one single point. So it's just a new technique of a derivative, which is not much different than stuff we've already done. Now over here it gets a little bit harder because we have x's and y's mixed, so we got to watch the product rule. And we're also asked another question where we're finding where dy dx does not exist, so it's kind of like a domain issue question. So let's start with the derivative. The derivative of 2x squared is 4x. Now I'm going to do product rule for the xy term. The derivative of the x is 1 times the second plus, I leave the x the same. The derivative of y is y prime, minus the derivative of y squared is 2y times the derivative of y, which is y prime, equals 0. Sometimes it's really easy to forget that there's a -7, and instead of writing -7, you have to make sure you're taking the derivative of the -7, which is 0. Okay, we want to group the y prime terms together and move everything else over. So 4x plus y equals -xy prime plus 2y prime. I factor out the y prime. These steps don't change. They kind of stay the same in every example. It's just a matter of getting the y prime terms together and the y term, everything else on the other side. I finally isolate for y prime by dividing both sides by minus x over 2y, or minus x plus 2y, and this represents my slope of the tangent. They say to find the value of the derivative at a point, so y prime at my point is 4 times -2 plus 3, which is -8 plus 3 is -5. Minus a -2 is 2, plus 2 times 3 is 6. So -5 over 8 is the value of my derivative at the point. And now dy dx, or y prime, does not exist when my denominator is 0. So I'm going to go minus x plus 2y has to equal 0. So that's going to be whenever x is equal to 2y. Now we could go back and actually sub everywhere we see an x, sub it in as a 2y and solve. So I'll show you how to do that, but we're not going to actually finish going through it. But you may be expected to do this as well. So 2x squared plus xy minus y squared equals -7. We have a relationship here of when the derivative is not going to exist. So 2 times 2y squared plus 2y times y minus y squared equals -7. So 4y squared plus 2y squared is 6y squared. Let's work this out carefully. 2 times 4y squared plus 2y squared minus y squared equals -7. 8 plus 2 is 10. 10 minus 1 is 9. Y squared equals -7. Now you're going to notice that y squared can never equal a negative value, so there are no points where the derivative does not exist. Now, sometimes you may get a solution from here, but in this case we don't. But if you were, you would be able to write the coordinates for the point where the derivative doesn't exist. Okay, this one is your turn. I'll let you try that, and the solutions will be posted. Okay, let's look at this one. Find y prime if the function is x cubed plus y cubed equals 6xy. I should be careful about calling it a function. It might be a relation because we have to make sure it passes the vertical line test. Way back earlier when I skipped this slide over here, you'll notice they talk about the folium of Descartes, and it's a very specific example. And in that very, very specific example, this thing here is not a function, so I shouldn't be really calling it a function. I should be really calling it a relation. Okay? It's just a relationship between x and y in this formula. Okay? So let's go back. We're going to take that folium of Descartes, and we want to find the slope of the tangent line through that folium at a very specific point, which is 3, 3. So let's find y prime first. 3x squared, I'm taking a derivative, plus 3y squared. You've got to remember we're taking the derivative of y, which is y prime. And then I'm going to do product rule on this term. I'm going to treat 6x as one function and the y as the second function. So the derivative of 6x is 6 times the second plus, you leave the first one the same, derivative of the second is y prime. And you'll notice these steps are quite repetitive. You just have to make sure you're watching your algebra. So 3y squared y prime minus 6x y prime. So you'll notice I'm moving that term to the left equals, now because I move the y prime terms to the left, I'm going to move the minus 3x squared to the right by subtracting, plus 6y. You'll notice that both of these terms have a y prime. We're going to factor it out. You get 3y squared minus 6x equals this stuff here. And then y prime equals minus 3x squared plus 6y over 3y squared minus 6x. So I don't mind if you don't simplify this, but it is required of you to solve for dy dx every time. So on your assignment, if they give you an example that says find dy dx and its implicit differentiation, you must actually get the dy dx by itself. Y prime at the point now, this is part B, is you just sub the point in, so minus 3 times 9, because 3 squared is 9, plus 6 times 3 is 18, divided by 3 times 3 is 9 times 3 is 27, minus 18. And so you'll notice the numerator is minus 27 plus 18, and the denominator is 27 minus 18. So you literally get the answer -1. Okay, and you'll notice here that they've actually subbed it in and worked out the solution for us as well. Okay, this last example, you can see that there's a graph provided using Desmos. This graph is not the graph of a function, it's the graph of a relation. They have the solution here for you, so I would like you to try this example. It is a little bit trickier to solve for dy dx. I'll kind of do the first step for you. When we're differentiating this term, we're using chain rule. So the derivative of sine of some value is cosine of that value times, now because of the chain rule, we need to do the derivative of the inside, which is 1 plus y prime, which equals, now this becomes product rule, so the derivative of y squared is 2y y prime times cos x, plus we leave the first function the same, the derivative of cosine x is minus sine x. So I'm just going to briefly walk you through this without doing the entire example. You're going to take this term and distribute it out, and once that's distributed out, you're going to take this negative and change that to a negative. And then you're going to move the y prime terms over to one side, leave the other terms on the other side, factor out the y prime, and then solve for y prime. So it's usually the same 3 steps, and you'll notice that that's exactly what they do here, and then you get this function here which they've worked out. Okay. Now the very last question, I do want to go through this one. It is slightly different than the ones we're used to. Now in here they're asking us to find the second derivative. So it requires us to find the first derivative first. Derivative of x to the fourth is 4x cubed. Derivative of y to the fourth is 4y cubed. But now because there's a y term we're differentiating, we take the derivative of y, which is y prime, and the derivative of 16 is 0. Now we will have to simplify this function and solve for y prime, but instead of doing that first, I'm going to do one more derivative. So the derivative of the term, 4x cubed, is 12x squared, plus, now this requires product rule again. The derivative of 4y cubed is 12y squared y prime, and then I have to multiply by the second function, plus I leave the first function the same. The derivative of y prime now is y double prime. I take one derivative of a derivative and I get the second derivative, equals 0. Now anytime you see these terms with a y prime in it, it is expected we get the y prime and sub that in from that previous step. So when I solve for y prime from this previous step, which we're going to do, okay, I'm going to kind of do it a little bit quickly. I'm going to move that term over and then divide by 4y cubed. I'm going to get minus 4x cubed divided by 4y cubed, and so therefore y prime would equal minus x cubed over y cubed. And then every time I see this y prime term, there and there, I sub in the value that I've just found. Okay, so 12x squared plus 12y squared, I sub in my y prime once, sub in my y prime again, plus 4y cubed, y double prime equals 0. Remember, my goal is to solve for y double prime, which is right here. So I'm going to clean this stuff up, this term. So my, let's use a different color here. So my y squared will cancel with the 3 of those and have 1 left over. And other than that, nothing really happens. So 12x squared, minus and a minus makes a plus. There will be a 12 on the outside. X, now we don't multiply these 3's, we add them because they're exponent rules. So x to the 6, and on the bottom I'm going to have y to the 4th equals, now I'm going to also move this term to the left, which is negative 4y cubed y double prime. So finally we're going to end up dividing by minus 4y cubed on both sides, but I'm going to do that by first simplifying the numerator term out, which is this term right here. I'm going to make a common denominator. So 12x squared y to the 4th plus 12x to the 6th over y to the 4th. That's the common denominator for the numerator, minus 4y cubed for the denominator. And now I'm going to just do my kiss and flip, or multiplying by the reciprocal. 12x squared y to the 4th plus 12x to the 6th divided by y to the 4th. That becomes 4 over 1, so this will become 1 over negative 4y cubed. And then finally, when it's simplified out and done, I'm going to get x squared y to the 4th plus x to the 6th all over y to the 7. You're going to notice I'm not paying attention to the numbers. These 3 numbers will simplify because I can divide them all by a negative. Well, we'll leave the negative on the bottom, but we'll divide all those terms by 4. So 12 divided by 4 is 3, 12 divided by 4 is 3, 4 divided by 4 is 1, and then I left the negative there. And this would literally be my final answer for dy dx, provided I didn't make any careless mistakes, which I've been noticing I've been doing. So, and then you can notice that theirs looks a little bit different than ours, but if we were to factor an x squared out and a 3 out, we would get the exact same expression shown below. So that's the second, oh, whoops, and I shouldn't call this y prime because it's not. This should be called y double prime. Okay, So that, hopefully, in a nutshell, represents implicit differentiation. The key idea here is coming way back from this slide that talks about when you're differentiating where the variables agree, you just do the derivative normally. If the variables don't agree, then you have to have this additional y prime term every time you differentiate a y term.